Good day, my name is Alexander Andelkovic. I work as an agile testing lead at King. Today I'm going to be talking about how King uses AI to test Candy Crush Saga. King was founded 2003, has made over 200 games and have around 2,000 employees spread on 11 locations around the world, and we have around 271 million active monthly users. And we were acquired by Activision Blizzard 2016. Candy Crush Saga is our biggest game, and we are also making a lot of other games in the casual puzzler genre. At King, the game teams can choose what type of QA roles they want to have in the team depending on their needs. ATL, the Agile Testing Lead role, main purpose is to coach the team to deliver quality. The persons within the teams are all responsible for quality. And the QA analyst is an exploratory tester within the team. Usually they are the experts in reproducing repro scenarios when there's like a bugs. They also help out with feature testing when it's done. QRT, quick regression teams, they are responsible for, before a release, testing all main features, making sure that they're okay. They usually have 8 hours to test around 1,000 test cases. Test automation engineer are a developer role, and they are responsible for making automation frameworks that the teams utilizes. Data scientists, they are also helping out with making sure that the data looks okay and are not polluted. So they're testing the data that we collect. And then the developers, they're responsible for unit tests and also some integration tests to try to automate them. And also they are helping out when we have team test activities. King has been looking into the field of AI to see if it can be of any use for us when we produce games. We were always trying to achieve highest quality. And one project that we had was where we tried to make a test automation bot powered by AI, BAIT. And the idea was that the bot should take screenshots of the game and then use AI to detect the different buttons and then click on the buttons and then do some kind of verification after the button has been clicked. The workflow is that BAIT engine is communicating with a automation framework and asking for screenshots. And after the screenshots has been taken, the BAIT compares it with if there are similar screenshots. If not, it's considered to be a new state. So we update like a game graph with the new state that the bot are visiting. And then we do a check to see that everything is okay at this screen by pressing a button. And then after that, we do this again in a loop. And then we run through the game until there's no more buttons to press. We have like a list of all detected objects, and then we check them off as being visited when we press them. We use something called synthesizing imaging method approach to train our AI to detect the different components, because the graphics that we use are a little bit unique. We have our own style. So to train an AI to be good at detecting something, it's good if you have a lot of samples. So what we did was that we took some screens and then we cloned them, we duplicated them and changed their sizes, their rotation, coloring and stuff like that to get more samples to train the data. so that the AI would be better in recognizing the different components. One thing that we noticed, a takeaway, was that if you have backgrounds with a lot of different colors and different graphics, it can be difficult for the AI to detect the components it has been trained for. So what we did was that we applied an algorithm called mask RCNN, and that algorithm filters out everything besides the objects that we're interested in detecting, and that increases the accuracy of the detection algorithm. Another thing that we did was also that we had problems with the fonts where the letters look very similar, like the letter 3 and the letter 8. It was just like 2-3 pixels that separate them. So what we did was that we made it simpler for the detection algorithm by reducing the amount of colors and also the pixels, so that we get just the bare minimum that's needed for the algorithm to detect the different letters. And we used various image manipulations algorithms to do that, and they are part of an open source library called OpenCV that are free to use by anyone. And results you can see here. The screen on the left is the screenshot that we take when we start the game, and then the screenshot to the right have rectangles around the objects that AI has been able to identify after we have trained it. To be able to determine if the screen that you visit are the same or a new one, we need to apply a similarity detection approach. So one thing that we did was that all of the identified objects, we gave them a separate identifier so that we can distinguish between them. And then we used an algorithm called Euclidean distance algorithm. With this algorithm, you can measure the distance in similarity between different objects. And if it is the same object, the distance is very close, and if the similarity is not that big, then the distance is farther away. And what we do then is that we have a threshold. If it is close enough, then we consider the different components to be the same object that we are seeing. And the same approach we applied for texts that are in our game. So we're using the Google Vision API to extract the text strings. And then we use an algorithm called TF-IDF vectorizer to reduce the amount of similar words. So we just have text strings with unique words, and then we give them weights, and then we compare those weights to see if they are close to each other or not. So if you have like a phrase that has weights that are within a similar distance, then we consider it to be the same text. If it's two different texts, the distance between them are too big, and then we're considering it's not the same text. So how do we use this? So in the first case to the left, you can see that there we have a screen that are the same screen. And how do we know that? Yes, because we look at all of the identified objects, and with this image similarity algorithm, we will see that all of the objects are close to each other, that means that it's the same objects, and it is within this a threshold that we have that are determining if it's the same screen. In the second option, there's like a bug. This black box is covering the screen that we took, but we're still at the same screen. So the way we detect that we still are on the same screen, even though there are graphical differences, is by using the text similarity algorithm. And with that, we can see that all of the texts are the same. So that gives us the confidence that we are still on the same screen, but we have found some kind of visual bug. And to the right, where we go to a new screen, the way we see that is by all of the graphical elements are very different from the new screen, and the distance are above the threshold that we have. And then we use this text similarity algorithm also to increase the confidence level that we are in a new screen. And the same thing there, we can see that there are a lot of text strings that are not the same at all, and they're above the threshold that we are required for it to be considered the same screen. So with the high confidence, we can say that we have reached a new screen. With this approach, what we challenges and benefits with it. One challenge is when you are at the same screen and you have animations. There you can get false positives because the screen are moving and the distance might be outside of the threshold, making the algorithm think that it is visiting a new screen. So to address that, what we did was that we hard-coded those screens to not be detected by the algorithm. A good thing was that with this approach, if there are alignment errors, you will detect that for free because it will flag for some difference within the screen, and then you can see that it is an alignment error. Another thing was to have to tweak the threshold because the background are different. So even though we are on the same screen, the algorithm can think it is in a new screen because the background are different. But with some tweaking, you can get it to still think that it's in the same screen. Same thing with overlapping menus. You're at the same screen, but it's a new state because the menu, you have new options there. So same thing there. You need to have a table where you can add, depending on the threshold, that this screen are different because when you press on the components, different actions happens. So when bait goes through the game, it creates a graph. So for every new screen it detects, it adds it to this graph that are representing the traversal for the game. And it is a little bit like a logging to see what has been performed. And we were curious to see if we run this on 4,500 levels, how would this graph look like? And here you can see it. And of course, this is not useful. So you need to have some filtering to be able to use this, to make this graph useful. Also, the game, to be able to communicate with the bot, with bait, it needs to have an interface. And the thing that the bait are interested in are to be able to win a level or lose a level, because it's not designed to play the actual game. It's designed to test everything around the game. And the same thing for saving time. We can unlock levels so that it can progress quick to a certain area in the graph. Start to test there. And same thing with some features that needs where you need to play normally. You can unlock it so you can test it immediately. And the same thing with accessing Facebook. It can do that with a Facebook token. One thing that we found a bit useful for was to detect missing texture. That is time consuming for human eye to sit and watch and trigger a lot of screens to be able to see it. And the missing texture is this pink square. It should be some graphical representation there, but because some kind of linking problem, you see this pink square instead. So the way we detect the algorithm that detects the pink square, it's designed to first filter out the coloring and then just save the contours of the picture. And then we're using an OpenCV function to found the contours. And then depending on a certain threshold, the amount of pixels with the same color, we use a function called contour area that returns a number telling how much similar pixels are close to each other. And there we have like a threshold, and if it's above this threshold, it's not considered to be like a filled in space. And if it's below, then we know that this is probably like some kind of pink square area, and then that one is flagged as a missing texture. And here are some examples where we use it, and you can see that there are it can happen everywhere, and so it's been really useful to help to iron out those type of bugs. We can also use this approach to identify missing texts. Same thing there. There's some kind of linking problem, so we just have the label for the text and not the actual text. And the same thing here, we can find by parsing the identify text, and if it has these brackets, that's flagging that this is not the actual text. It can also be used to find alignment problems with the text. The Cloud Vision API returns a bounding box around the text that it detects. And what you can do then is to see if there are overlapping bounding boxes. So that's also like an indication that you have some problem with the positioning of the texts. Another thing that we found was useful was you can also find visual animation bugs, like in this screen. What you can see here is that the particle effect should be behind the transparent layer, but it is not, and it was picked up by the algorithms because the threshold was higher than anticipated. And what we have done for Bait to be able to communicate with the game, we have integrated a web server that over HTTP can take REST commands and in debug mode. So the game are communicating with Bait over HTTP, and we're sending the commands for mobile and desktop. For the thing that the bot wants is the game to send a screenshot. It wants to be able to tap at a certain coordinate on the screen, and it wants to be able to finish levels and also log into Facebook, where the game do it for the bot. And when we have the bot up and running, how do we scale it up so more people can use it? So what we did was that we built like a web page where user can start bait jobs and then also see results from the jobs. So it's a basic page where you pick a game that you want to play, that the bot should play, and then you pick what type of detection that you want it to do. In our case, it's a text detection and missing texture, and we will add more stuff depending on the needs. And then you pick the build that you want to run on. And when you have done that, the bot is scheduled to run, and after it has been running, you can see in a graph what it has performed, and that is very useful when if you want to debug and see what was done prior to some issue. And so after running bait for a while, the takeaways that we have, the things that it's very useful for is finding crashes, because you can run bait in parallel. So you can have more testing time and more coverage than you normally do with human testers. So it's a really good complement from that perspective. And as described before, finding text bugs and also the graphical issues like these missing textures is very useful from that perspective to help out. And also if audio errors, you can check for that. And there are also like performance, you can measure performance between every action and see if there are any increased CPU usage or memory, so you can get profiling of the game while the bait is running. Yes, so that was it about bait. And if you have any further questions about how to get started or about the things that I talked about in this presentation, feel free to reach out to me on my email. I can say that we are doing various AI projects at King. So this is what we're doing for QA, and we're doing other projects as well, where we are looking at the gameplay itself. How can you use AI to measure how good the levels are? So that's another AI project that we have. And also we are also looking into other areas where the users interact with the game to try to understand that in a more systematic way. And also, if you want to get started with this, I would recommend that start small, hire maybe some kind of intern from the university that have been studying machine learning, and give them a small project to start off with. That should only take around 3 to 6 months to do like a proof of concept. And then after that, you should evaluate that and see if you want to continue with it. AI is a nice thing if you can find a problem that it's useful to solve. So you shouldn't use it just because of the hype. That's a big takeaway from our experience using AI. And we have done it we started around 2016 with it. So we have done it for a couple of years. And it can take time also, depending on your needs, I would say. All right. Thank you very much for listening to this presentation. And I hope you have a continued nice day. Thank you very much.